Welcome to my talk about sum rules via large deviations for polynomial potentials and the multicut regime, which is about the joint work together with Fabrice Gamboa and Alain Roux. And to give a general idea what this talk is about, we are going to show large deviation principles, so concentration of measure phenomenon, for weighted spectral measures of random matrices. And such a large deviation principle comes with a rate function I, or here it's I1, which measures in a probabilistic sense the cost of deviating from the limit. And we're actually going to show this large deviation principle in two different ways, using two different encodings of our random measure. And if we do this in the second encoding, we arrive at a different formulation for a rate function, I2. But of course, a large deviation rate function is unique, and so as a corollary to these two different methods of proof, we obtain such an equality between these two different formulations for the rate function. And this equation turns out to be an important relation in the spectral theory of Jacobi operators, which is called a sum rule. So to begin with, we choose our n by n random complex Hermitian matrix according to such a density. So it's a unitarily invariant distribution defined through some potential v, which of course has to satisfy some assumptions. I'm not going to list these assumptions here. But you can just imagine v being a polynomial of even degree and positive leading coefficient, and then everything works. And the random objects we are interested in now is the spectral measure mu n of this pair xn and the first unit vector, which is defined by this relation. So the kth moment of this spectral measure mu n is the first entry in the kth power of this matrix xn. And a bit of linear algebra tells us that then this measure mu n looks like this. It's a finitely supported measure. It's supported by the eigenvalues of the matrix xn and with weights wi, which are defined through the eigenvector matrix u. So this is a weighted version of the empirical eigenvalue measure, which puts mass 1 over n in each eigenvalue lambda I. And as n tends to infinity, it's not hard to see that mu n has the same limit as the empirical eigenvalue measure. So it converges to some limit mu v, an equilibrium measure, which is compactly supported by one or several disjoint intervals. And then we have the following result, which is a generalization of an earlier theorem where we had to assume that the support of mu v is a single interval. We don't need to assume this here. So we obtain that mu n satisfies a large deviation principle with speed n and such a rate function, which is only finite if the support of mu is equal to the support of mu v, the equilibrium measure, plus an at most countable set E. And in this case, the rate function consists of these two parts. The first part is the Kullback-Leibler divergence of mu v with respect to mu. And for the second part, we sum over all points in this set E, and we plug in these points into functions fv, which are given like this. So this fv is the effective potential just standardized so that the infimum over all these values equals 0. So you might recognize this fv as the rate function in the large deviation principle for the largest or smallest eigenvalue. And indeed, we also see this rate function here. We have to plug in all the points which are in this extra set E. So this is our first large deviation result. And for the second one, we now look at a different encoding of our random measure mu n. And this encoding is through its recursion or Jacobi coefficients, which can be defined like this. So let's say we have a probability measure mu with compact and infinite support. And then we can define a sequence of polynomials orthonormal with respect to mu. And these polynomials satisfy a recursion like this. And in this recursion, we see these coefficients ak, which are strictly positive, and bk, some real number. And so we obtain a sequence b1, a1, b2, and so on. And the measure mu is uniquely determined by this sequence of coefficients. Now, of course, for our random spectral measure, this is finitely supported. We cannot define a full sequence of orthonormal polynomials, but we can define polynomials up to a certain degree. And this defines the first 2n minus 1 of these coefficients, so b1, a1 up to bn. And for our choice of randomization, we also know the distribution of this vector. So this was shown by Krishnapur, Raida, and Virac, that this vector has a density which looks like this. It's proportional to e to the minus n times trace of V and now apply to a tridiagonal matrix Tn, that's an n by n matrix, where we put the b's on the diagonal and the a's on the off diagonal. And then there's also a logarithmic term appearing here. So now we can use this explicit density and we can use a nice decoupling trick, which was also utilized by Breuer, Simon and Zaitouni, and we arrive at the following result. So this is now a large deviation principle where we have to assume that V is a polynomial. And in this case, we obtain, again, a large deviation principle with speed n, and the rate function looks like this. So it's the limit of, and now you see here, essentially a standardized version of what is here in the exponential, where we center by V of Tn of mu V. So this is the n by n tridiagonal matrix when we plug in the Jacobi coefficients of mu V, of the equilibrium measure. And similarly here, ak of mu V is the coefficient of the equilibrium measure. And then we also have this extra term psi n, and unfortunately we don't know explicitly what psi n is, but we can at least bound it. So we can show that if we have some information on the support of mu, so let's say it's contained in this set minus k to k, then psi n is uniformly bounded. If the support of mu v is a single interval, so this is the one-cut case, in this case this extra term goes to 0 and then we can just omit it in this formulation of the rate function. In the multicut case, however, this is not an artifact of the proof, so it's really necessary in order to have a well-defined rate function, and we think that the role of this extra term psi n is here to distinguish between measures which can be obtained by permuting these Jacobi coefficients. So this is our second large deviation result, but of course both large deviation principles were for the same sequence of random measures. So we obtain this equality between the two formulations for the rate function, which looks like this. And this is what's known as a sum rule. And in this sum rule, it's important to note that both sides can be finite or infinite, but both sides are simultaneously finite or infinite. And so as a consequence, you can obtain from this sum rule equivalent conditions for finiteness of either side, expressed through spectral information, so looking at the left-hand side, or expressed using the Jacobi or recursion coefficients, looking at the right-hand side. The most prominent sum rule for probability measures on the real line is the one due to Killip and Simon, and indeed this sum rule reduces to the Killip-Simon sum rule if we choose this quadratic potential, which corresponds to choosing our random matrix according to the Gaussian unitary ensemble. Since then, many generalizations of this Killip-Simon sum rule have been proven, for example, by these authors, however, usually in a different formulation, because this formulation up here is the one we obtain from this probabilistic approach via large deviations. It's important to note that here we do require V to be a polynomial, because otherwise we cannot show this second form for the rate function. And now the big question is, of course, what happens if V is not a polynomial? We can show that in particular cases this equality is still true, but we don't know if this is true for general potential V. This is what I wanted to tell you. Thank you very much for your attention.